So this session's number 6 in the series of 12 workshop discussions around economics. We're going to talk about biophysical data. It should be a relatively brief presentation today. So before we get started, just want to acknowledge the traditional owners and the land in which we meet and the land that we're going to talk about. Pay my respects to elders past, present and emerging. And let's talk about biophysical data. So click on that. Okay, so to give us some context again about the collective economics platform. So there's 4 parts to this. So there's the first, and the one that we're focusing on today, is Eco-nomics Plan. So that is a lumped catchment scale tool used for prioritisation, investment prioritisation. Then there's Eco-nomics Project. So this is farm scale project capture and modelling. And then related product is about being able to communicate. We'll do impact reporting around those proposed or implemented projects. And then the 4th part is about being able to facilitate the use of those projects in environmental markets. So we're going to talk about Eco-nomics Plan. So this is about this lumped sub-catchment scale modelling approach. So it's about rapid investment portfolio generation. The audience for the output here is for investors, and the users of the tool are investors, NRM bodies and local government authorities. We want to have consistent approach across large spatial scales. We're proposing to base this on the approach used in reefonomics, and we covered that in an earlier session. And it's including quantitative and qualitative measures. So, and today we're just talking about the quantitative component related to the biophysical modelling. So the basic approach of how Eco-nomics Plan works is we start off with, we call the base data. So we want to have an area available to do some work. And then we also have the underlying load or condition of the measure that we care about. This might be suspended sediment, this might be DIN, this will be some other measure that we care about. Then we have an action. So this action might be to grazing management to increase end of dry season cover. So we apply this action over an area of grazing, and it has some impact. It might have a big reduction in fine sediment and a little bit in DIN, and it might actually go the other way for some other action. So effectively, we apply the action, we do some accounting, modify then the available area we've taken it out of service, and we manage the loads on these things. What goes along with each of these elements is confidence. So we have confidence in the underlying load or condition, so where that data has come from. So some things are great and they're well measured, others not so much, and we have to use a proxy for them. So we can represent the confidence in the underlying data. We also represent the confidence in our ability to predict the change on that underlying condition. Some things we know well and we have a high level of confidence, some things not so much. And that confidence gets propagated through as well in the accounting process. So we get a predicted result and we get a confidence in that predicted result. So that's how it works. So from the session earlier this week about quantifying the action effectiveness for quantitative things. So these are principally our water quality related measures here. There's 3 different methods in here. So we're doing a fixed change. So this is from like point source activities, wastewater treatment plant upgrade, where we have a fixed tonnage reduction. We have a yield change. So it's a reduction per area. So kilogram per hectare or kilogram per kilometre for linear features like streams and gullies. And then we have an efficacy based approach, which is a proportional reduction. So this is for things like a filtering action like a riparian buffer strip. So it might have a 20% reduction on the collective hill slope erosion arriving at the stream. So if the hill slope erosion load decreases from other actions, we're not taking a fixed amount out through the riparian work, but a proportional change. So that's cool. Ultimately, and we talked on the earlier session about how we would capture those effectiveness measures. So today is really about thinking about the base data back in this diagram, this base data of representing the area to do work and the load or condition, just for the biophysical stuff. And the pilot case for Eco-nomics Plan is the Southern Queensland landscapes. And we're fortunate enough that the state government has got three source water quality models that cover that area. And so we propose that we'd use that as the base data. And as came out in the very first presentation, there's actually quite good coverage across New South Wales and Victoria of source water quality models as well. So in this case, we're using it for the Southern Queensland landscapes case, but we hope that we'll be able to replicate this process elsewhere because there's similar level of quality of data. So this is a quick summary of how source kind of captures information, if you like, and how we can use it. So the hashtag SC, so in source language, this is a subcatchment. It's the base spatial unit that's used for hydrological and related water quality modelling. They're typically small units, but they vary from model to model, but they might be 50 to 100 square kilometres. In Eco-nomics Plan, and as we've done for reef-onomics, we aggregate those up to a subcatchment level. And that subcatchment represents we call them a planning unit. So we deal with that spatially. So then within each source subcatchment, there are functional units. So when we think about functional units, just think about it as a land use. So we've got, in this particular model, grazing, both open and forested, conservation, cropping, both dryland and irrigated, horticulture, forestry and urban. And so each one of these small source subcatchments can have all of these, and we know the area of each of those. So in the base data, this is what we use to represent the available area to do work. So when we are applying actions of grazing management in open country, we know the total area available, within each subcatchment because it's been captured in the source model. And then for each one of these functional units, there's a series of different processes that can be applied. Not all of them apply in all cases, but effectively they're all available in the hierarchical structure that source provides. So we've got diffuse dissolved, channel remobilisation, hill slope, point source, stream bank and gully as ways to generate constituents, they call, so the underlying measures that we care about. And in this particular model and in most, these are the common measures or constituents that get represented. So dissolved inorganic nitrogen, DON, and particulate, dissolved organic phosphorus, I guess, filterable react phosphate, particulate P, fine and coarse sediment. So with that collection, effectively we can use this example at the bottom. So we can apply an action to an area. So that's represented by the functional unit, and do work to adjust the measure, this constituent, by targeting a particular process. So it's constituent by process. So to make that a bit less vague, so we have grazing management in open pasture action. We can do work on the grazing open available land, and we can reduce all of the constituents that are generated by the process of hill slope erosion. So we're increasing cover So effectively decreasing the hill slope erosion rate, and as a consequence, it dials down all of these constituents that are generated via that process. So that's what we're proposing as the base biophysical data to use in Eco-nomics Plan in the Southern Queensland landscape implementation. And I suggest we'll probably be able to generalise that elsewhere. It's effectively in the Eco-nomics tool, and it sort of works as intended. So we're halfway through this collective long session. So we've got some biodiversity data discussion coming up on Monday, and that will be principally around the appropriate vegetation layers to use. And then mid next week, we're talking about business as usual. So how to account for declining condition in the absence of doing different actions. We'll post this video where the others are, economics.net.au/videos. Thanks. Well, let's have some questions.